Good afternoon, everyone, and welcome to the last talk in the operations track today. It's scaling Kubernetes to thousands of nodes across multiple clusters, calmly, I hope. Let's see. Please make sure to move into the rows so everybody that's coming in right now can get a seat as well. And also, remember to rate the session after the talk. Now to the introduction of our next speaker. Ben is a software engineer at Airbnb. He has worked with database scaling, Ruby and Node.js performance, and incident response, and of course Kubernetes. So with that, let's give Ben a big round of applause.
Yeah, thank you. Like he said, I'm Ben Hughes, and today I'm going to talk about how we at Airbnb contended with massive internal adoption of Kubernetes that led us to quickly scale up past single cluster limits. I've been at Airbnb for over 7 years, working on various areas of infrastructure and scalability. So much of what we consider our current legacy infrastructure, I often remember when its predecessor or predecessor's predecessor was shiny and new. So it's kind of an interesting bit of context to have when designing new things. So let's first cover the basics. For those of you who aren't familiar with Airbnb, Airbnb is one of the world's largest marketplaces for unique, authentic places to stay and things to do, offering over 7 million accommodations and 40,000 handcrafted activities, all powered by local hosts. And today, I will talk about how we scaled our Kubernetes usage. I'll start with how our architecture evolved and got us using Kubernetes. We were a migration case rather than greenfield. So we're talking about moving existing services rather than just supporting newly created workloads. Then we'll check in on what the practical scaling limits for Kubernetes clusters are and how rapidly we were approaching them. And these limits, combined with our growth, led us to look towards multiple clusters. Of course, simply creating a bunch of clusters isn't really the hard part. Like with most things, it's maintenance and ensuring consistency that end up being the greater burden. We've invested in tooling and strategies to keep this under control while also integrating with our existing infrastructure. So finally, I'll talk about how we try to enable change and evolution within the system. Any new thing can hopefully account for the use case at the point in time that it is written, but use cases change. This is especially important because the Kubernetes ecosystem is complex and fast-moving. So whatever structures you have around it have to be able to account for change. Plus, you're pretty much guaranteed to screw up some seemingly insignificant config that comes back to haunt you later. So how did we get here? I think the story of how our architecture evolved is a pretty common one for tech companies of this decade. We started with a single monolithic code base that did absolutely everything. And it was a Rails app, so we called it Monorail. It turns out that everyone who has a large Rails app at the center of their business calls it Monorail. I was crestfallen when I discovered that we weren't so creative. And this was fine for a while, but it became rather unwieldy. As the number of engineers grew, it became more and more of a choke point. This single large code base that could do absolutely everything also made it hard to reason about boundaries. Monorail was honestly just a huge slog to work with. Luckily, there's a solution for this. Services and service-oriented architecture were there to save the day. You know, piece of cake, guess we can all go home. And at first, we only had a few services, and they were extracted for specific performance, library, or isolation needs. But then it was an absolute explosion of services. We really took micro to heart. And over the course of a couple of years, we added hundreds of services. This had advantages over the monolith, and it allowed development to be unblocked, but it wasn't an unqualified win. On the developer experience side, engineers were now required to touch many, many things to roll out certain application changes. Things like the actual application code, chef configuration of their systems. And this was made way worse because we were managing many secrets via chef data bags. Things like Terraform or alerting rules. This just was generally a pile of pull requests. Many of them even had to be deployed in a specific and often non-obvious order. So this is the initiative this led to an initiative to reduce the many touches to one touch. And this is where Kubernetes comes in. But also a lot of other tooling to wrap around Kubernetes. We didn't just give people kubectl apply -f and tell them to have fun with it. And Kubernetes provides the integration point so that all of an app's config can live with the app. This capability continues to grow as we use more and more custom resources and custom controllers to manage things beyond just the distribution of containers. Our goal is to enable all app and config changes for a service to be a single PR, a single code review, and a single deploy. But hundreds of services is probably still too many. Like, keep it under control. And of course, so we had stood up a system to handle all of these services. We still needed to get all those services on the system. So we began migrating existing services. This was initially an unproven thing, so initial migration was very slow. Teams just started to dip their toes in. We were also more likely to get smaller deployments of smaller, somewhat less complicated services. But as this built up momentum and as teams got more comfortable with this, the migration continued more rapidly, and we started to see larger services coming over. And around this time, we started to think about questions like, what are our scaling limits? And at some point, the calculus shifted from how can we get stuff to use our thing to what happens if all this stuff is using our thing. And initially, any limits or issues seemed pretty far off. So I joined the internal Kubernetes team in September of last year. And at the time, our main production cluster had about 450 nodes. While I was coming up to speed, I had a number of conversations about what sort of projects to work on. And someone mentioned that we should start thinking about multi-cluster. So, I kept it in the back of my mind while working on other stuff. But by December, we had doubled to 900 nodes. So how big can we make these clusters again? So we turned to the reference documentation. There's a hard limit at 5,000 nodes according to the official docs. OpenAI had a great blog post on what they had to do to get to 2,500 nodes. And reading between the lines on that, scaling to 2,500 nodes is something worth writing a blog post about. And we also had various conversations and generally got the message that you develop a lot of new problems after about the 2,500 to 3,000 node range. Of course, more recently, Alibaba did some really great work and published a blog post about how they were able to get a cluster up to 10,000 nodes. A lot of those changes are actually seem to be pretty generally applicable. So I'm really excited for how this will push forward Kubernetes scaling going forward. But at the same time that we were pondering what our theoretical future scaling limits might be, we also had some sudden, more pressing questions like, would it be bad if our etcd were suddenly getting out of memory killed? And it turns out this question was not hypothetical. So as we closed out last year, we were having a lot of issues with etcd getting backed up and falling over. All it took were small shocks like a lower cache hit rate on the API server or a flurry of events to cause etcd to get overwhelmed. It's really easy to cause a flurry of events in Kubernetes. And luckily, when the control plane failed like this, it just stopped any deploys or scaling activity in process. It didn't take down our workloads. So it's not great, but it's still better than everything falling over and the entire site being down. And the good thing is that a lot of these etcd issues were just caused by hitting up against limits in the etcd v2 data format. Once we upgraded to the etcd v3 data format and did some other things like adjusting quota backend bytes up to 8 gigabytes, most of our etcd problems went away. We also had some issues with scheduler latency when evaluating really complicated anti-affinity rules, but luckily we were able to simplify many of those rules and also upgrade to newer versions of Kubernetes that came with a lot of optimizations. So we effectively got a taste for the problems that came with scale, but we were still rapidly scaling up. By March, we had doubled again to 1,800 nodes, and the team was working hard to ensure capacity. And we needed a plan to cross 2,500 or even 5,000 nodes. So we went with the obvious solution of standing up multiple clusters. When you can't make a single cluster any bigger, we must make more clusters. So in April, we had capped out at about 2,300 nodes in our production cluster. And we would not grow the prod cluster beyond this point. We found some substantial improvements in place where we were able to free up some capacity, and we started diverting workloads to newly created clusters in May. So Multiple cluster was the solution that we had been considering since I had started on the problem. And it's the solution that we went with, and it's been very effective for us. And at the same time, multi-cluster can be a bit of a loaded concept. People mean a lot of different things when they say multi-cluster. And other decisions or considerations in your organization can make it easier or harder. So when you're splitting up, things up into a whole bunch of clusters, you need to think about the specifics of your problem space. Are there placement restrictions on your workloads? That is, do certain services need to be in the same cluster or kept very far apart? And this may be the case if you're using cluster DNS or Kubernetes service discovery, or doing a lot of communication over an overlay network. And moreover, what problems are you trying to solve with multi-cluster? In our case, we were primarily targeting pure node count and cluster size. But if you're trying to do things like isolate workloads or take advantage of multiple clouds or cloud burst or anything like that, you'll need to make different decisions. And there are efforts in the Kubernetes community that are underway, like KubeFed or Federation V2, that target they seem to target kind of a superset of a lot of these concerns and a lot of like these sorts of related areas. They can potentially solve a lot of these problems. And we're excited to see how these efforts continue to develop. And I think we'll be able to use a lot of the tooling that comes with this, but it's not currently something that we've incorporated. So overall, with these considerations, we got lucky, and we're able to pursue a fairly simple version of multi-cluster. And a big thing, like probably the biggest thing that we got lucky on was that the particulars of our service mesh, smart stack, and our migration case caused us to need first-class communication between our legacy EC2 infra and our new Kubernetes services. And this avoided co-location requirements. So as services were getting migrated, a request might come into EC2 and then get routed to another service in Kubernetes, then route it back out to EC2. We even had services that while they were migrating were in kind of a halfway state where they were running half their capacity on EC2 and half of it on Kubernetes. And so basically any workload can run on any of the clusters that we stand up, basically. And our view of clusters sees them as just giant pools of compute and memory to be allocated as we see fit. And so while this is, and we do have one restriction just to kind of simplify things, and that's that our services run on a single cluster. And we select that cluster at the time that the service is created. So at the time an engineer is setting up the code structure for their brand new service, they'll run a command and it'll actually bind them to a specific cluster that they will get assigned to. And this of course can be changed later, and we have tooling to handle migration between clusters. But the big reason we have this restriction, and I don't think we'll have it forever, is that it prevents us from having to rewrite a lot of tooling or write a bunch of wrappers around things like kubectl or kubedashboard to pull in state from all the places where a service might be running. But I think the service mesh is something that's worth drilling in on a bit more. So here's a diagram to try and illustrate what we're doing. And we run our pod network on an overlay network, and this is either flannel or canal, depending on which cluster we're on. And the overlay network is restricted to the cluster itself. So this would prevent, so you can't communicate with pods on other clusters over this overlay network. Or you can't go from EC2 instances to pods on any cluster over this overlay network directly. So to get around this, and this was completely just for the way that we were doing our service mesh and service discovery, we use a lot of node port services running in local mode. So your application would be listening to port 80 on your pod IP, and then the node port service would configure a high number port on the node IP, and through the magic of IP tables, the traffic would get routed from the node IP import to the pod IP import. And since this is running on the nodes that are local to the pod, or to the node that is local to the pod, this gets rid of bounces through a gateway ingress tier like ELBs or Nginx or things of that nature. And that avoids us having to constantly be bouncing things around or keep sort of ingress tier allocated and working. So in effect, we're using node port services to make our pods routable on virtual private cloud subnet addresses, which is something that can be accomplished in a much more straightforward way by using VPC CNI plugins like the ones from Amazon or Lyft. And with these, pods just get IPs directly from the VPC subnet pool, and you can achieve flat network between nodes, pods, and random instances. This involves far less IP tables, and it's very appealing. So we're strongly considering using one of these going forward. And so that's what we have. We don't really care where services are run. There's not much to guide their placement. And for simplicity's sake, we assign a cluster at creation time. And we then allow those clusters to grow to a certain size. Currently, we cap that at about 400 nodes. And then we're like, OK, no more services get assigned here. But this still leaves plenty of headroom to allow us to continue scaling up the cluster as service needs scale. And the general idea is to avoid the hard problems of large clusters by not letting clusters get large. And we do also have some specialization amongst clusters for things like test, development, and special applications like machine learning. So let's look into how we manage our clusters. So it turns out, when you aim to have a lot of clusters, you're going to need to create a lot of clusters. And it's not a one-time task. These are clusters that you are now responsible for maintaining. And that includes keeping them consistent. So in terms of creating and to some extent managing clusters, there are existing projects like Kops and KubeAdmin. These are great tools, and if they work for you, that's fantastic. Kops especially is pretty upfront about being opinionated, and some of these opinions ended up not working particularly well for us. We specifically needed to integrate our Kubernetes nodes with our existing tooling around EC2 instances. And we didn't want to hard fork our underlying infrastructure and have to reinvent or relearn everything about managing just EC2 instances. And the instances shouldn't be completely different just because they happen to be running Kubernetes rather than some other service. We also wanted to make sure that we solved the full problem as we saw it. So what even is a cluster? It's certainly nodes. And all those nodes need to be configured. Packages installed, SSH keys, the works. A cluster isn't that much without etcd to store its state. And you need to configure all of the options that go to the various components of the control plane. You also need to set up things with your cloud provider like IAM roles, DNS configuration, ASGs, whatever. All of that stuff needs to be configured somehow. And it's Kubernetes, so you need certificates. The genius of Kubernetes, of course, is that through it, all problems can be turned into either public key infrastructure or networking problems, which, as we all know, are the easiest problems to debug. And so for this type of config, we generate Chef and Terraform code into the appropriate existing places. But this isn't all that makes a cluster. If I were to hand you a cluster with all of these set up, it still wouldn't work. So much of the behavior of the cluster is dictated by cluster-level services that are expressed as fairly normal Kubernetes API objects. And these include things like CNI, DNS, metric server, and the like. And these are the things that show up in your tutorials as kubectl applying random YAML from GitHub. We don't want clusters to get configured using randomly applied YAML from GitHub. This is kind of like when sysadmining involved a lot of ad hoc apt getting onto individual pet servers. Cluster services are also very much like any other workloads we run. And ideally, we would deploy them using the same deployment tools we use for everything else. And the development process should be familiar to engineers working on any other service. We also want to make sure that a cluster is never missing a component, and that components stay up to date on all clusters. So we solve this by making all cluster-level services into a single deployable unit. The deploy system rolls it out all at once. So you don't deploy core DNS separately from kube2 IAM, for instance. It's all in one package. We also deploy to entire tiers of clusters in the same action. And this prevents individual clusters from falling behind simply because we forgot to deploy to them. We don't want prod 1 to get all of the latest goodness, while prod 3 just kind of sits there, a month out of date, just because no one triggered the deploy there. And so deciding what goes into this unit is pretty straightforward. If the service needs to be local to the cluster, things like daemon sets, deployments, like core DNS, Kube dashboard, other things along those lines, then it can go here. Otherwise, it's just a regular service, and it can go to whatever single cluster it's assigned to. And so we refer to this collection as Kube system, after the namespace where a lot of these things happen to live. So the actual deployment process is a mix of things, but it does lean heavily on Kubernetes. Much of the core config is structured as Helm charts, though we mostly use Helm as just a template engine. And we pull all the dependency Helm charts together using an umbrella chart and template into a single manifest that we then apply. Then there's a few stages where we synchronize IAM roles, and then we have a number of apps that use KubeGen, which is our internal Kubernetes sort of framework. And this tool is primarily around generating manifests, but it does also have some imperative deploy logic and things that kind of guide the deploy process, so we have to handle that separately. And since this is a collection of many different things, partial failure is always a possibility. So we try to make this predictable. And so we try to deploy as fully as possible. We can't make it fully transactional or atomic, so we prefer to continue the deployment even if some unrelated components experience errors, rather than bailing out on the first failure. This is kind of similar to the approach that Terraform applies tend to use. Okay, so we have clusters, and we have configuration for them, and we have the services that run on clusters. We need a bit more structure on top of this. We want our prod style clusters to be alike. We also want our test or dev or like anything that we have multiple clusters for. We want those to be kept similar and to share as much config as possible. So we introduce a layer of cluster types on top of this. So prod 1 and prod 2 share the cluster type of prod. So cluster types are like classes, while clusters are like instances of those classes. Since we're using clusters solely for horizontal scaling, clusters of a cluster type should be nearly the same. And ideally, as a user who's deploying their service to one of our clusters, you shouldn't really be able to tell what cluster you're on. And we really want to avoid people trying to land their services on the good cluster. So by trying to make all of our clusters the good one. And all of this together makes the cluster launch process a matter of using scripts to generate Chef, Terraform, and Kube system code. We then get that code reviewed and merged, and then cause the etcd and Kubernetes nodes to be launched. And finally, after this, we deploy the Kube system artifact, which for this cluster, it will be the initial deploy of that and cause everything to get set up. And at the end of that, we should have a fully working cluster. This entire process takes under an hour, and a fair amount of that time is actually just getting a sign-off on the changes to the IAM roles. And we stopped trying to optimize beyond that because we're not doing this so commonly that further optimization would be particularly beneficial. So this makes launching clusters relatively easy. But the real test for us involves adapting to changing circumstances and accommodating new use cases. So when we made the change easy, we saw that we got more change. We reduced barriers, and things started happening much more rapidly. So we pretty quickly learned some of our initial assumptions were wrong. And originally, our Chef, Terraform, and Kube system code generation was one shot. You generated the set of output configuration once at the time of cluster creation and made further modifications in place into the files that you generated with the generation script. If you wanted to change anything broadly, you had to update both the generators so that anything newly generated would get the new version, and then you also had to go back and apply the changes to all the things that had been previously generated. And these things might have drifted in the intermediate time as people may apply changes in place. And we ended up having to do this a lot more than expected. And it was really sort of causing us to put off implementing new features because we didn't want to figure out how to apply them to existing clusters. So this pointed to a continual regeneration process. So what we did was we separated out the config into a bunch of high-level config files that serve as inputs. And then these feed into the generators, and the generators fully regenerate all outputs on every run. And so this prevents drift, makes it easy to add features, and separates out the interesting variable configuration from all of the boilerplate. So of course, now that we make it easy to apply change to existing clusters, some change is relatively easy to apply. If you update a Kubernetes deployment, Kubernetes will figure out how to make those changes and apply them. So you're good to go there. But even stuff like upgrading Kubernetes is fairly straightforward. There's an ordering that you have to do. You have to you upgrade the masters, rotate those out, upgrade the minion nodes, rotate those out. But it's a change that's meant to be applied. It's probably something you actually want propagated. You can get from state A to state B fairly easily. But not everything is like this. Networking, in particular, is very sticky. It's very hard to change things like CIDRs or CNI plugins in place on a running cluster without disrupting workloads. It's possible that you can do it, but one wrong step and everything kind of falls apart. It's much easier just to move workloads between clusters. So it would be bad if our new total generation scripts caused us to switch existing clusters to a new CIDR that we wanted to use. So one concept that we're experimenting with in our configuration is having the ability to fix values for things that are hard to change. So we fix these values in the configuration at the time that the cluster is created. And we can then change the way that the value is derived for new clusters without having to change it for old clusters. So we could, if we wanted to fix the node CIDR mask size at 24 in clusters when they're generated, we could do that and then change that value going forward. And eventually, the older clusters can be rotated out and replaced. So another thing is that we want to be able to step out of the user's way when they have a use case that we can't or don't support. I've certainly not thought of every way that our users might want to use Kubernetes or what sort of clusters they might want to create. And certainly not thought of every configuration that can be expressed in either Chef or Terraform. So I really don't want to get in the way of what our users can do. So we want to let them drop down and modify the code that would otherwise be generated and overwritten. So every comment that we generate, or every file that we generate, has a comment at the top of it that can be marked to prevent overwrites from happening. And this has proven very useful as people are doing, frankly, a lot of very weird stuff in Kubernetes land. So definitely allows them to have their fun without us having to accommodate it in our generators. So this is an ongoing process. And Kubernetes, as you know, Kubernetes, its ecosystem, and our usage of it are all quickly changing. And so we're trying to incorporate learnings as quickly as possible and fuse them together to create a more maintainable system, figure out what needs to be generated, incorporate features as soon as they're available, all of this stuff. And we need to be able to also roll those out to all of our clusters. So this has unlocked our continued scaling. And where we're currently at is that we have 22 cluster types, so 22 different sort of use cases for that. A lot of these are fairly experimental, and we're doing a lot of work to sort of prove things out. And we'll see where that leads. And these represent 36 clusters, many of which are part of the prod cluster group, which is expanding to support our actual service workload. And altogether, this represents over 7,000 Kubernetes nodes. And the exciting thing is that from our current strategy, we see no upper bound on the number of nodes that we would be able to support. We can just continue creating more clusters to support the increased capacity needs. So yeah, Thank you all for your time, and you can learn more about our engineering work on our blog at medium.com/Airbnb engineering, and we are also hiring. So head over to careers.airbnb.com and come work with me. Thank you very much.